Hey there, welcome back to 2241. This is the examples 2 video for section 2.1. We're continuing with problem number 7 here. All right, so find vector functions parametrizing a toroidal spiral and a trefoil knot. Now, these are relatively hard exercises, but I wanted to walk through them so that you can start to get a little bit of an idea of how more complex parametrizations might work. So a toroidal spiral, we saw a picture of this earlier, kind of goes around a donut in a shape like this. There we go. And it's actually probably easier if we parametrize the whole torus first. Now, the torus is a surface. Draw a picture of it. It should look something kind of like this. Draw it a little cleaner. Something kind of like this, like a donut. And then we can think of the toroidal spiral as sort of traveling around the torus in circles. So the torus has sort of a coordinate system on it. Works like this. And we want to parametrize that entire thing. And like I said, it's a surface, so it's going to need two variables. One to go around the arm of the torus, and one to go around the outside. All right, so let's shrink this guy, and then we'll draw an XYZ coordinate system and try to figure this out. Okay, so our torus will go up there to remind us what we're looking for. And we want some parametric equations for this guy. One way to think of the torus is that it is a circle being dragged around a circle at right angles to it. So we have a circle out here somewhere in space, and it gets dragged around and then back. So how do we parametrize that? Well, that picture I just drew gives us a little bit of insight. So our torus is going to consist of maybe two vectors here. One going there, one going there. And then I want all of the vectors around in a circle here, or going around in a circle here. So the coordinates of this circle in a plane, let's say, are, let's say this is the YZ plane, because our torus kind of looks like that. It's oriented like that in standard form. So we've got y of t, x of t, z of t, and I'll pretend x is 0 for a second. And then in the y, let's say for convenience that this vector has length 2, and this vector has length 1. So we have 2 plus, and we want our vectors, let's say we want our parametrization to start here, just like a standard circle, and go around counterclockwise. So we want our vector 2 plus, let's say, the cosine of t. So this is acting like our x coordinate in the xy plane now. And then in our z coordinate, we're going to have, all right, not changing anything here, sine of t. All right, and that's to go around that. Okay, so what do we want to do now? Well, we want to rotate this all the way around the XY plane. And we want to think of the range of values, the range of radii going from 2 - 1 to 2 + 1. So we want to think of this, actually, the y-coordinate, as the radius of the torus at different values of certain parameters. So these are the ranges of the radius. All right, and now let's call these big R of t for a second. So now if we have a circle in the xy plane, circle in xy, we know that parametrization. And here, we're going to use a different variable of parametrization. So s is not equal to t. X of s is, how do we want to do this? Well, I want my circle to be, I'm sorry. I want my circle to be starting at the standard position, let's say. And we want cosine of s, and y equals the sine of s. And then z just 0. Okay, so circle in the xy plane is given by that. This is a cylinder. And how do we put these together? I want the radius to be that. So I need to modify this circle by putting a radius in front of it. We can do this. Okay. Well, then we get our parametric equations in two variables, x of t comma s equals 2 plus the cosine of t times the cosine of s, and then y of t comma s equals 2 plus the cosine of t times the sine of s. Okay, and then now while this is happening, I want z to be moving up and down, but I don't want it to depend on s just yet. So it will be, let's say, the sine of t. That's where this part comes in. Okay, so now we have our parametric equations, and I'm going to go ahead and erase a lot of this, and then get our toroidal spiral from it. Okay. Our range of radii, get rid of our drawing here. And this goes over here. Okay, so there's our parametric equations for a torus. And let's think about this for a second. I now want to specialize this torus, or this parametrization, to go in a spiral around this guy. Like that. So how do I do that? Well, in order to do that, I have to remember that t controls this part of the torus, and s controls this part of the torus. So if I can relate those two things together, I can get them to move in sync, and now I can draw circles on the surface of the torus. So relate t and s. And we want to do this linearly, actually. So relate t and s, and we actually want to do this linearly to get a nice, smooth, constant spiral. And easiest way to do this, let's just say that t equals some constant multiple of s. I don't know, let's say 2s, or maybe 3s. So every time s goes around once, t will go around 3 times. Or maybe we want more than 3 actually then, in that case. No, 3 should be fine actually. So we're not looking at pi times s. All right. Yeah, so given that, we can turn our torus into our toroidal spiral given by x of t equals 2 plus cosine of 3s times the cosine of s. Oh, I wrote x of t, didn't I? X of s, y of s equals 2 plus cosine of 3s sine of s, and z is sine of 3s. And there we go. There's our toroidal spiral. If you go ahead and graph these equations in like Desmos or something, you should get a toroidal spiral. Okay, let's move on now to the trefoil knot. This one is tricky. So remember what the trefoil looks like. It's this shape that kind of does some weird stuff. Like that. And there we go. So it kind of wraps around itself. What do we do with this guy? Well, we kind of have to take some liberties with how we think about it. We want to embed it into 3-dimensional space. And, well, we can kind of see that, again, it's a rotating thing. But we also have to take into account the z motion. So I want it to go up and then down and then up and down and so on. And I got to be careful about that. So let's position it like this. Let's say that the x-axis goes along one arm here. We're going to do this in 2 dimensions first. Look at the projection of the trefoil, and then we'll understand, or we'll figure out how to fix the z-axis part afterwards. Okay, so I want something to start out here, and then as it goes around in the angle, I want it to decrease its radius, but not to 0. I want it to have a minimum radius here. So I want it to go around, decrease the radius a little bit, and then increase back to its maximum radius at another angle. What angle should that be? Okay, so if I draw a quick mock-up of what I want my trefoil projection to look like, I want it to do this, and then is that quite right? I want it a little further actually. More like this, and then I want it to come back out. Okay, I want it to go like this, and then I want it to back out and have a maximum there, and then go back in and have a minimum at 2 pi. And then it's going to come back out and have a maximum out here, go back in, and that's not particularly accurate, more like this, minimum, and then come back and meet there. Okay, so what are these angles that I want? Okay, so at 0, I want maximum radius. And at, let's see, what does this look like? Maybe 5 pi over 6, I think. 5 pi over 6. I want the minimum. And then at 4 pi over 3, I want the maximum again. Okay, so how do I get this to work the way that it should? I'm sorry, not 5 pi over 6. 2 pi over 3 right here. That's what I want, 2 pi over 3. So I want this to have period 4 pi over 3. Okay. So erasing all of this. We want a very specific set of equations. So again, we're going to go around. We have our x of t, y of t, z of t. So x is going to give me, okay, cosine of t. I want it to go around, starting there. And then y is sine of t. And we'll deal with z in a minute. But we have our circle, and now I want to modulate the radius. So move this guy over, and now I need a radius function. That r of t is what we're going to look for now. So I want my radius to vary between a couple of things. I want it to, I want it to not go in too far, and I want it to also have a maximum. So let's make it similar to the toroidal radius over here. So the radius of the toroidal spiral, we had this constant plus a cosine term. That should work just fine. And then we can do 2 plus, just like before. So r of t will be 2 plus cosine of, well, what should go in here? Well, we can think of a slightly different period or slightly different relationship between t and s. So it's actually something on the torus. It's just a different toroidal spiral. So what are we going to do here? We want our spiral to be a little bit more shallow. So we don't want our spiral to rotate around the torus really quickly. We want it to go slowly, then come back around, and then rotate again. And we want it to sort of not match up for a while, but sort of as little of a while as possible. So I'm going to suggest that we want 3t over 2 here. And let's think about why this is. Why does 3t over 2 work? Well, we want our radius to have a period of 4 pi over 3, right? We want to go all the way around here before getting to a max again. And then a min halfway in between. Does that work? Well, if t equals 2 pi over 3, what do we have here? Well, we get cosine of pi. 2 pi over 3 and 3t over 2 cancel out, and I get cosine of pi is -1. That's the minimum of cosine, and thus the minimum of my radius function. Well, what happens at t equal 4 pi over 3? Well, I get cancel with this, and then I get cosine of 2 pi, which is again 1, which matches t equals 0, 1. So our radius function works with that as our frequency. All right, and that is what's going to go into our parametric equations right up here. So our trefoil gets the equations. Let's move this over, not erase it. 2 plus 3t or 2 plus cosine of 3t over 2 cosine, and 2 plus 3t or cosine 3t over 2 times sine. Okay. Now we figure out what's going on with c, and well, you can actually guess that it doesn't really matter because we're still just tracing on a torus here. So this matches up with the toroidal spiral over here. We're just choosing a different frequency that is a little bit shallower. And so what you can do then is you can actually take the toroidal spiral, or the torus, I suppose. Let's call it the torus here. And change the frequency to some rational number over here. It should be an S, shouldn't it? Yeah. I forgot what I was trying to do. Cosine of S here, and then same down here, cosine of A over B S, sine of S, and then sine of A over B S. So you can change the values of A and B to get various spirals. So the trefoil itself is a toroidal spiral, just with a fractional frequency on the inside. So you can experiment and do things like 4 over 3 or 5 over 2, see what happens there. All right. So we'll do this next one, and then we'll do the other examples in a final video. So draw the projections of the twisted cubic onto the coordinate planes. Then find equations in x, y, and z for them. Okay, so the twisted cubic is actually, I'm just going to go ahead and copy it so I don't have to redraw things. Remember, it is this shape right here. And I've already kind of given you one of the projections. Copy, move over here. Ooh, too far. Okay. So here's our copy-pasted twisted cubic. And if you remember, I actually showed you what the projection on the ZX plane looks like. I want those to be yellow. ZX. So if we come over here and kind of look at this, you can see, all right, well, it's kind of going up, 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 up. Like this maybe. And then over here, it's kind of going down, 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 down. Ah, all right, so the projection on the ZX plane looks something like this. And we have what looks like a cubic equation. Okay, so that's the ZX projection. And what about the YZ and XY projections? So maybe we should do the XY projection, I think. Okay, yeah. the xy projection should be fine. So move these around. And the xy projection, we erase this, now looks a little bit more like this, and like this. And oh, that looks like a parabola to me. So that's our sort of shape that we're going to draw here. So we have a parabola in the xy plane. All right, let's do this one more time. And this time with the YZ plane. And this is going to be a little bit weirder. Y. And the projection in the YZ plane, that looks kind of strange, doesn't it? So it looks more like, it's kind of going up and then it's going up here. And then it's doing the same thing, but in the other direction for this back curve. So it kind of looks like something with a cusp there, or a corner maybe. It's a better way to say it. Okay, so if this is a cubic, well, it's got a pretty easy equation to write. Then z equal x cubed, right? And then over here we've got a quadratic. We'll just say it's y equal x squared. Okay, cool. So that's 2 out of 3 projections. And now we need an equation for this last guy. Well, that relates y and z, and I have equations with z and x and y and x. I can eliminate x from both of these. Here's an easy way to do that. So I can square this to get z squared equal x to the 6th, and I can cube this to get y cubed equal x to the 6th. But then I have x to the 6th in both equations, so here I have z squared equal y cubed, and that is my equation in z and y. So this curve right here is a bit of a weird one. It's a y to the 3/2 power equation, except it is both the positive and negative square roots of it. And so our next video will conclude the examples.